Hi guys, today I'm going to go over this 1981 free response problem that I had assigned to y'all a while back, and this will be for test review. So the way this problem reads, it's telling you that there's some solid ammonium hydrogen sulfide, and then that's going to break up into or decompose into ammonia gas and dihydrogen sulfide gas. And it tells you that after equilibrium is attained, that the total pressure inside the vessel is found to be this 0.659 atmospheres. So what they want you to try to find out is the value for Kp. It first says to write the expression for Kp and then calculate its numerical value. So what you need to be thinking of is ice chart, and then when we get to our pressures, our equilibrium pressures are going to add up to equal this total. So let's do that now. Let's go ahead and set up the ice chart. So my initial change in equilibrium amounts, it doesn't tell us what the equilibrium, what the initial amounts are. It just says that there's some solid NH4HS that's placed in a vessel. So we would start out with this amount, and then the amounts for the others would be 0 and 0. Their change would be plus x and then plus x, because looking at the stoichiometry, these would each have coefficients of 1, so this is plus 1x and plus another x. So your equilibrium amounts are going to be x and x. If we set these equilibrium amounts and we add them together, okay, their total pressure is going to be 0.659 atmospheres. So why, might you ask, are we ignoring whatever pressure we might have for the solid? Well, part of that is because the solid is never going to play a part in the equilibrium, and also a solid can't have a pressure. Okay, so that might have been a little bit tricky for you, but all we're going to concentrate on are the pressures for the ammonia and the dihydrogen sulfide gases. So if these two pressures add up to equal 0.659, then if we simplify the left side, that's 2x equals 0.659 atmospheres. So if we divide both sides by 2, then x is going to equal roughly 0.330 atmospheres. Okay, so then the problem asks us to write the expression for Kp and calculate its numerical value. So on the left side, I'm going to do that. My Kp expression is going to equal my concentration of ammonia times the concentration of H2S, and because this is a solid, I'm going to ignore my reactant in that expression. So this is just my Kp expression. Calculate its numerical value. Well, I'm going to plug in 0.330 for each of these. Okay, 0.330, and I'm going to solve for what Kp equals. And I get 0.109. Okay, now I rounded to the third decimal place. Kp is going to have no units, so this is my answer for part A. Okay? Alright, and then whenever we read this next part, part B, it says, okay, well now there's some extra ammonia gas injected into the vessel, and then when equilibrium is reestablished, then the partial pressure of ammonia is twice the partial pressure of H2S. So then we have to calculate the numerical value of the partial pressure of NH3 and H2S at equilibrium. So we set up our ice chart again, and I'm going to refer to this reaction once more. And as I'm looking at this, I have, so let me rewrite this reaction real quick. So I know this is a solid. We have ammonia plus H2S. And so after equilibrium is reestablished, the partial pressure, okay, so this is, if we have our ice chart, this is going to be the equilibrium values, okay? So equilibrium, partial pressure of NH3 is twice, so that's going to be 2x, whatever x is, twice the partial pressure of H2S. And we didn't change our temperature. Notice that our temperature is still 25 degrees Celsius, and what does that mean about the value for Kp? Well, conveniently, the value of Kp did not change. So, we're going to set Kp, which is equal to 0.109 again. That's going to equal our expression, which is ammonia times dihydrogen sulfide gas. So we're going to set this equal to 2x because we don't have a value for it, times x, okay? And so if we simplify the right side, that equals 2x squared. Left side again is still just 0.109. And then we're just going to solve for x. Okay, so we take both sides, we divide by 2. X squared is going to equal 0.054. Okay, and then if we take the square root of both sides, x is going to equal 0.233. Alright, so when we plug that back in, H2S partial pressure is going to be 0.233 atmospheres. And the partial pressure of ammonia, we would then need to multiply it times 2. So 0.233 times 2 is 0.466. And there we have the partial pressures of each of these substances at equilibrium. Okay, so then in this part of the problem, it tells us we have a completely different experiment. We have ammonia gas, and we have this dihydrogen sulfide gas again introduced into an empty 1 liter vessel at 25 degrees Celsius. Notice that that's the same temperature that we've been at all along, so we know Kp is still the same value of 0.109. And excuse me, the initial partial pressure of each gas is 0.5 atmospheres. So we know that when we set up our ice chart, and I'm just going to ignore this left side, that the partial pressure initially is 0.5 atmospheres. And the change is going to be minus x, because now we're starting out with these substances and none of the solid. And then it's going to want us to calculate the number of moles of solid NH4HS. Well, this is not going to be possible using the ice chart. We're going to have to use our stoichiometry. But first we have to figure out what our equilibrium values are for the pressures of partial pressure of NH3 and H2S. So, if you look previously, when we had solved for the amount for x, when Kp is 0.109, x equaled 0.330. So we're going to take 0.5 and we're going to subtract out x to find out what our equilibrium pressure is. So 0.5 minus 0.330 is going to give us a partial pressure of approximately 0.17 atmospheres. Okay, and that's what each of these pressures are for each of these substances. Okay, so if this is the pressure for ammonia, which is also going to equal the pressure of H2S, well, we can conclude, because these are all in a 1-to-1 mole ratio, that this is also going to equal the partial pressure of NH4HS. Even though a solid can't really have a pressure, that's going to be its amount relative to the others so that we can calculate for moles. Okay? So we can use that same amount. So in order to find the moles is going to equal, according to the ideal gas formula, PV equals nRT. Oh yes, it's bringing this in. The number of moles is going to equal pressure times volume over RT. So our pressure is the partial pressure of any of these because they're all in a 1-to-1 ratio. So I'm going to write this in red so it'll show up. This is going to equal 0.17 atmospheres. Okay? The volume conveniently is 1 liter. We're going to divide by R, which is 0.08206. And then our temperature is 25 degrees Celsius, but we know we have to add 273 to that to get it in the Kelvin temperature. So that's 298. So when we solve for what the number of moles is, we get, wait for it, okay, we get 0.00, looks like a 7 after it's rounded, moles. Okay, and that's going to be the moles of solid ammonium hydrogen sulfide. Okay, and that's the answer. Now this looks kind of crazy because they wanted you to remember this part up here for the amount of change when Kp equaled 0.109. Seems a little tricky to me, but that's how to solve this problem. I hope that